It's a crisp autumn evening on the Virginia coast. The sun has just set over the Wallops flight facility, casting long shadows across the launch pad where an Antares rocket stands ready for its most critical mission yet. Tonight, this towering vehicle carries more than just cargo. It carries the hopes of NASA's commercial space program and supplies desperately needed by astronauts aboard the International Space Station. The countdown reaches its final moments. Mission controllers monitor hundreds of data streams as the engines ignite with a thunderous roar. For 6 brief seconds, everything appears normal. The rocket rises majestically from its platform, trailing a brilliant plume of fire and smoke. Then, in an instant that would be replayed millions of times across the globe, everything goes catastrophically wrong. This is the story of the Antares Orb 3 mission failure. A disaster that would expose decades-old secrets, reveal the hidden dangers of Cold War technology, and forever change how we approach commercial spaceflight. October 28, 2014 began like any other launch day at NASA's Wallops flight facility on the eastern shore of Virginia. The Mid-Atlantic Regional Spaceport buzzed with activity as teams conducted final preparations for what should have been a routine cargo delivery to the International Space Station. The Antares rocket, standing 133 feet tall and weighing over 530,000 pounds, when fully fueled, represented the cutting edge of America's commercial space program. Developed by Orbital Sciences Corporation under NASA's Commercial Resupply Services contract, the Antares was designed to fill a critical gap left by the retirement of the Space Shuttle program. With the shuttles grounded, NASA needed reliable partners to ferry supplies, experiments, and equipment to the space station. This particular mission, designated Orb 3, carried over 5,000 pounds of precious cargo in its Cygnus spacecraft, scientific experiments worth millions of dollars, fresh food for the astronauts, spare parts essential for station operations, and student projects that represented years of hard work. The launch window opened at 6:22 p.m. Eastern Time, with perfect weather conditions greeting the mission controllers. Clear skies, light winds, and excellent visibility created ideal circumstances for what everyone expected to be another successful flight. This was, after all, only the 5th launch of the Antares rocket system, which had maintained a perfect safety record through its first 4 missions. As the countdown clock ticked towards 0, thousands of spectators gathered at viewing areas around the facility. Families of NASA employees, space enthusiasts, and members of the press watched with anticipation to life. The familiar AJ-26 engine's roation as the rocket's twin rumble of rocket engines echoed across the Virginia coastline, as 760,000 pounds of thrust lifted the vehicle from its launch pad. For those first 6 seconds, everything proceeded exactly as planned. The rocket climbed steadily skyward, following its predetermined trajectory with precision. Mission controllers watched their screens intently, monitoring telemetry data that streamed back from hundreds of sensors throughout the vehicle. Engine temperatures, fuel pressures, guidance systems, and structural loads all appeared nominal. But hidden within the thunderous symphony of rocket engines, something was going terribly wrong. Deep inside one of the first stage engines, a critical component was beginning to fail in a way that no one could have anticipated. The failure was silent, invisible to the sensors, and devastating in its consequences. At exactly 6 seconds after liftoff, as the rocket cleared the launch tower and began its arc toward orbit, disaster struck. A massive explosion erupted from the base of the vehicle, sending shockwaves across the facility and creating a fireball visible for miles. The rocket, now transformed into a falling inferno, began its deadly descent back toward the launch pad. The range safety officer, trained for exactly this scenario, had only seconds to react. As the crippled vehicle plummeted earthward, the destruct command was transmitted, ensuring that any remaining fuel would be consumed before impact. The explosion that followed was so powerful it could be felt in Pocomoke City, Maryland, over 20 miles away. Debris rained down across the facility as emergency crews rushed to secure the area. Fortunately, the automated safety systems had cleared all personnel from the danger zone, and miraculously, No one was injured in the catastrophic failure, but the loss was staggering nonetheless. Years of scientific work, millions of dollars in cargo, and months of planning disappeared in those few seconds of destruction. The failure sent shockwaves throughout the space industry. Here was a rocket that had performed flawlessly on its previous missions, operated by one of the most experienced companies in the business, launching under perfect conditions. How could such a catastrophic failure occur with seemingly no warning? As investigators began sifting through the wreckage and analyzing telemetry data, they would uncover a story that stretched back over 4 decades to the height of the Cold War space race. The engines that powered the Antares rocket carried with them a secret history that few people knew. These weren't modern American-built power plants, but rather Soviet-era engines, originally designed for one of the most ambitious and ultimately failed projects in space exploration history. The trail would lead investigators from the beaches of Virginia to the classified workshops of the former Soviet Union, revealing how technology originally intended to put cosmonauts on the moon had found its way into America's commercial space program. They would discover warning signs that had been overlooked, design flaws that had remained hidden for decades, and systemic problems that threatened the entire foundation of commercial spaceflight. The investigation that followed would become one of the most complex failure analyses in spaceflight history. Teams of engineers from NASA, Orbital Sciences, and independent contractors descended upon the wreckage scattered across the Virginia marshlands. Every piece of debris, no matter how small, was catalogued and examined for clues about what had gone wrong in those critical 6 seconds. Initial telemetry analysis pointed to a catastrophic failure in the rocket's propulsion system. The data showed normal performance right up until the moment of explosion, with no advance warning of impending disaster. Engine pressures, temperatures, and thrust levels all appeared within acceptable parameters until the very "it" was as if the rocket had been struck instant, everything went wrong. By lightning from a clear sky. But as investigators dug deeper into the wreckage, they began to uncover pieces of a much larger puzzle. The engines that powered the Antares rocket were not what they appeared to be. Branded as AJ-26 power plants and manufactured by Aerojet Rocketdyne, these engines carried within them the DNA of a forgotten chapter in space exploration history. The story began in the late 1960s, when the Soviet Union was locked in a desperate race to beat America to the moon. Deep within the classified facilities of the Kuznetsov Design Bureau, engineers were working on what they believed would be their ticket to lunar victory. The NK-33 engine represented the pinnacle of Soviet rocket technology, designed to power the massive N-1 moon rocket that would carry cosmonauts to the lunar surface. These engines were marvels of engineering, incorporating advanced metallurgy and innovative design concepts that pushed the boundaries of what was possible. Each NK-33 was hand-built by master craftsmen who took pride in creating power plants capable of withstanding the extreme forces of spaceflight. The engines underwent rigorous testing, with each unit fired multiple times to verify its performance and reliability. But the N-1 program was plagued by problems from the very beginning. Political infighting, budget constraints, and technical challenges combined to create a perfect storm of failure. 4 consecutive launch attempts ended in catastrophic explosions, each one more devastating than the last. The final failure in 1974 marked the end of Soviet lunar ambitions and sealed the fate of the NK-33 engines. When the program was cancelled, orders came down from the highest levels of the Soviet space hierarchy to destroy all remaining hardware. The engines, the rockets, the facilities, everything was to be scrapped to eliminate any evidence of the failed lunar program. But Nikolai Kuznetsov, the chief designer whose name graced the engines, made a decision that would echo through the decades. Rather than comply with the destruction orders, Kuznetsov secretly moved approximately 80 completed NK-33 engines to a hidden warehouse. There, wrapped in protective coverings and stored in controlled conditions, they waited in darkness for nearly 3 decades. The Cold War came and went, the Soviet Union collapsed, and still the engines remained hidden, their very existence known only to a handful of people. It wasn't until the mid-1990s, as Russia struggled with economic chaos and the space industry searched for new sources of revenue, that these forgotten relics were rediscovered. American companies, eager to acquire proven rocket technology at bargain prices, saw an opportunity. Aerojet General negotiated a deal to purchase 36 of the engines for just over $1 million each, a fraction of what it would cost to develop equivalent hardware from scratch. The engines were shipped to Aerojet's facility in Sacramento, where teams of engineers began the complex process of understanding and modifying 4-decade-old Soviet technology. Language barriers, missing documentation, and unfamiliar design philosophies created numerous challenges. The Americans had to reverse engineer systems they didn't fully comprehend, adapting Cold War-era hardware for modern spaceflight applications. Despite these obstacles, the modified engines, now designated AJ-26, performed admirably in testing. They delivered impressive thrust-to-weight ratios and demonstrated the reliability that had made them attractive in the first place. When Orbital Sciences was developing the Antares rocket, the AJ-26 engines seemed like the perfect solution for their first-stage propulsion needs. But there were warning signs that not everything was as it appeared. In May 2014, just months before the Orb-3 mission, an AJ-26 engine suffered a catastrophic failure during testing at NASA's Stennis Space Center. The engine exploded 30 seconds into what should have been a routine 54-second test firing, sending debris flying across the test facility and raising serious questions about the reliability of the Soviet-era power plants. The investigation into that test failure revealed concerning details about the engine's internal components, but ultimately concluded that the specific engine that failed had manufacturing defects that were not representative of the overall population. Corrective actions were implemented, additional inspections were conducted, and the engines were cleared for flight. The decision to proceed would prove fateful when October arrived and the Orb-3 mission prepared for launch. The Antares failure stands as a stark reminder that in the unforgiving realm of spaceflight, even the smallest defect can lead to catastrophic consequences. What began as a routine cargo mission ended in a spectacular explosion that illuminated the night sky and exposed fundamental flaws in how we assess risk when dealing with decades-old technology. The investigation ultimately traced the disaster to a turbopump failure in one of the AJ-26 engines, though the exact root cause remained elusive. Manufacturing defects, foreign object debris, and the simple reality of pushing 40-year-old hardware beyond its original design limits all played potential roles in the tragedy. Perhaps most troubling was the revelation that both Aerojet and Orbital Sciences possessed insufficient knowledge about the engines they were depending upon to reach orbit. In the aftermath of the disaster, the space industry was forced to confront uncomfortable truths about the hidden costs of bargain basement rocket engines. The Antares program was completely redesigned, replacing the problematic AJ-26 engines with modern Russian RD-181 power plants. The launch facility at Wallops was rebuilt from the ground up, and new safety protocols were implemented across the commercial space sector. Today, as we watch SpaceX rockets routinely ferry cargo and crew to the International Space Station, it's easy to forget the lessons learned from that October evening in 2014. But the ghosts of the NK-33 engines serve as a permanent reminder that in space there are no shortcuts to safety, and the past has a way of catching up with the present in the most unexpected ways.